Hi and welcome everyone to one more lecture of probability and statistics. Today we will learn about consistent estimator and its properties. First of all, definition of consistent estimator. If we have x1 to x2 till xn random variables and tn is a function of x1, x2 till xn, and this is a random sample of size n, and then it would be a consistent estimator of parameter r theta, which is a function of theta, if Tn, probability of Tn tends to r theta as n tends to infinity. That means if n is indefinitely large, then probability of Tn should tend to r theta. Then we can say that Tn is a consistent estimator of r theta. And I know this is quite a theory part and everyone wants to skip it, but you should know what assumptions are we making. We can say that Tn is a consistent estimator of r theta if for every epsilon greater than 0 and eta greater than 0, there exists a positive number n that is greater than m epsilon comma eta, and probability of absolute value of Tn minus r theta less than epsilon tends to 1 as n tends to infinity, and probability of absolute value of Tn minus r theta less than epsilon greater than equal to 1 minus eta for every n greater than equal to m, where m is some large value. Of n. This is the theory part and the assumptions that we made for consistent estimate. Now we should note these two things. First, that Tn, probability of Tn tends to r theta is a consistent estimator as n tends to infinity. But we are not talking about any finite n. That means we can't say anything about consistency for finite n. Second thing that we should note is that if we have a Tn that is consistent for r theta as n tends to infinity, then we can construct so many functions that are built of these random variables. That means we can make a new function Tn dash out of Tn only, n minus a, n minus b times Tn, and we can also write this as, we will divide numerator and denominator by n, then this will be 1 minus a by n 1 minus by n times Tn, and this will tends to Tn as tends to infinity, and this will also tends to r theta as n tends to infinity. In this way, by change where a and b are constant, so by changing values of a and b, we can construct infinite number of new consistent estimators for r theta. Next is invariance property. If Tn is consistent estimator of r theta and f is a continuous function, then f of Tn will be a consistent estimator of f of r theta. If Tn is consistent estimator of r theta, then nf is a continuous function, any continuous function, then f of Tn will also be a consistent estimator of f of r theta. We will use this property in some questions and some scenarios. Now, this is the most important part of our lecture, and for consistent estimators also. We talked about what is consistent estimators, but we still haven't talked about how we can find out that given function is a consistent estimator or not. It should follow two conditions to be a consistent estimator. First, that expectation of Tn should tend to r theta as n tends to infinity, and second condition is that variance of Tn should tend to 0 as n tends to infinity. If a function Tn follows these two conditions for a function parameter r theta, then we can say that Tn is a consistent estimator of r theta. Now we will solve some questions on concept of consistent estimators. Our first question is, show that in sampling from n mu sigma square population, that means a normal distribution with parameters where mean is mu and variance is sigma square, sample mean is a consistent estimator of mu. As we recently talked about the conditions for a function to be a consistent estimator of a parameter, first was that expectation of Tn should tend to r theta as n tends to infinity, and second condition was that variance of Tn should tend to 0 as n tends to infinity. So first we should prove first condition, that expectation of Tn, that is here is sample mean, should tend to mu. Now if every random variable is a part of this population, then we can say that expectation of xi will be equal to mu, because they are taken from this distribution and this distribution have these properties, and variance of xi will be equal to sigma square. Now let's see, sample mean will be x1 plus x2 till xn divided by n. This is our sample mean. Now, expectation of Tn would be 1 by n times summation I equal to 1 to n xi. Expectation of xi. Now, we know that expectation of xi is mu. So this will be equal to 1 by n summation I equal to 1 till n mu. Now we are doing summation of mu n times, then this will be equal to n mu divided by n got cancelled out, and this equals to mu. Our E of Tn is tending to mu. Now we have to find out variance. Variance of Tn. Now this Tn is equal to 1 by n times summation of xi. So variance will be variance of 1 by n summation xi square. Now we know that variance of a times x equals to a square variance of x. So 1 by n will come out as 1 by n square into variance of summation variance of xi. We already know that variance of xi is sigma square. So this will be 1 by n square summation sigma square I equal to 1 to n summation. Now we will add sigma square n times. So this will be equal to n sigma square divided by n square. Our variance will be equal to sigma square divided by n. Now, as n will tend to infinity, our variance sigma square by n will tend to 0, because 1 by infinity is 0. So this tends to 0. Therefore, this is fulfilling these two conditions. Then we can say that our sample mean is a consistent estimator of mu. Moving on to our next question. Our next question is, let T1 and T2 be consistent estimator of R1 and R2 respectively. Prove that AT1 plus BT2 is a consistent estimator of AR1 plus BR2, where A and B are constants and independent of population. Now, we are given that T1 and T2 are consistent estimator of R1 and R2. Then we can note this one thing, that expectation of T1 will be tending to R1 as n tends to infinity, and expectation of T2 will tend to R2 as n tends to infinity, and variance of T1 tends to 0 at n tends to infinity, and variance of T2 tends to 0 at n tends to infinity. Now, we have to prove that AT1 plus BT2 is consistent estimator of AR1 plus BR2. First of all, we have to prove that expectation of this will tends to this parameter as n will tends to infinity. Expectation of AT1 plus BT2. So this will be equal to A times expectation of T1 plus B times expectation of T2. As n will tends to infinity, this expectation will tends to R1 and R2. So this will be A R1 plus B R2 as n will tend to infinity. Now, variance of AT1 plus BT2. So this will be equal to A square variance of T1 plus B square times variance of T2. Now we already know that as n tends to infinity, variance of T1 will tend to 0. So in this case, this will be A square into 0 plus B square into 0, because both of them when n tends to infinity will tend to 0, and this will be equal to 0 as n will tends to infinity. Therefore, by looking at these two conditions, we can say that AT1 plus BT2 is consistent estimator of AR1 plus. Our next question is, if x1, x2 till xn are random observations of a Bernoulli variate x, taking value 1 with probability p and value 0 with probability 1 minus p, show that summation xi by n times 1 minus summation xi by n is consistent estimator of p times 1 minus p. Now, first of all, we are given the values of probability for x. If x is 1, then its probability is p, and if it is 0, its probability is 1 minus p. Second thing, we have to prove that summation xi by n, 1 minus summation xi by n, is consistent estimator of p times 1 minus p. Now, can you remember invariance property, where we said that if Tn is consistent parameter for r theta, then f of Tn will be consistent parameter for f of r theta if f is a continuous function. Now, look at p into 1 minus p. If this is a function of p, then it is a continuous function. Now, we have applied same function to summation xi by n and p. If we prove that summation xi by n is consistent estimator of p, then we can say that summation xi by n f of will be consistent parameter of f of p, where f of x equals to x times 1 minus x. We are thinking quite backward, but if we will start the question, then you will got understood that why we use. Let's say, assume that Tn is summation xi, then expectation of Tn will be summation expectation of xi. Now, if we will find out expectation of, we have already told that this is a binomial distribution, then expectation of x will be np and variance of x will be npq. Now, if we take 0 as a failure, then this is 1 minus p. Then we can replace q by 1 minus p. Now we are given expectation and variance, both of them. Now, expectation of t is summation expectation of xi, and xi is observation from binomial variate whose mean value is np and variance is np times 1 minus p, then we can say that expectation of xi. Now we can say that Tn will also be an observation of this because Tn is summation xi. Therefore, expectation of Tn will be equal to Np. Now, summation xi by n will be equal to T by n because T is summation of xi. Now, if we take this as T dash, then expectation of T dash will be equal to 1 by n times expectation of T, and expectation of T is Np, so this will be equal to P. And if we will find out variance of T dash, because T is equal to summation xi, therefore its variance will also be Np into 1 minus P. Now we know that variance of T dash will be equal to variance of T by n, because T dash equals to T by n. Now this will be equal to, we know that variance of Ax equals to A square variance of x. Then we can write this as 1 by n square times variance of T, and variance of T is Np into 1 minus P. So this will be P into 1 minus P divided by n. And as n will tend to infinity, this will tend to 0. Now, our expectation of T dash equals to P and our variance of T dash tends to 0 as n tends to infinity. So we can say that T dash is consistent estimator of P. Now, if T dash is a consistent estimator of P and f of x is x times 1 minus x, then f of T dash will be consistent estimator of f of P, and this is what we have to prove. So using invariance property, first we will prove that summation xi by n is a consistent estimator of P, and then using invariance property we can say that this expression will be consistent estimator of P times 1 minus P. That's all. We will meet in our next lecture. Thank you.